Yes, thank you. So I'll say something about cosmology and the history of modern cosmology in relation to the issues of realism and anti-realism. When I prepared this talk, I realized, but only too late, that this is a much too big and much too complex subject to cover in an oral presentation, but I have to try. So I will say something about the domain of cosmology, something about the concept of the universe. I will also look at the development of, take a look at a particular but very important part of the development of modern cosmology in the interwar years, the period in which the expanding universe and the finite age, so-called Big Bang universe, were introduced. And I will pay particular attention to one person, one of the pioneer cosmologists, Georges Lemaitre, for reasons that will become clear in a few minutes. And then I will also say, but only a little, about the nature of cosmological knowledge in relation to some arguments against realism in the area of the astronomical sciences, an argument forwarded by Jan Hacking several years ago. I will not say anything about the discussion in general concerning realism and anti-realism, which, at least to an outsider like me, is extremely complex and extremely confusing because apparently there exists such a large number of positions and such a large number of apparently very good arguments, pro and con. But let me introduce my talk by pointing out that traditionally the discussion of realism in the physical sciences have focused on micro-objects too small to be seen. In the first half of the 19th century, that might be atoms and molecules. At the end of the century, it might be the electron. Then a decade later, the atomic nucleus. In the 1930s, we have a discussion concerning the reality of the neutrino. And in the post-war period, in the 1960s, a sort of similar discussion concerning the reality of quarks. And these kind of discussions go on. I don't know what the best example for is today. It may not any longer be the Higgs boson, but one could mention the existence or non-existence of superstrings, for example. But of course, the discussion of realism versus anti-realism applies also to objects and phenomena on a very large scale that for some reason cannot be seen. For example, based on various theories on a lot of seismological data, the geophysicists tell us that the inner part of the Earth consists of a solid inner core surrounded by a fluid outer core. Should this be interpreted as a claim that this is really what the constitution of the interior of the Earth is? Or is it only that we have reasons to believe that the Earth is as if it contained a core of this kind? Again, although astrophysicists are today convinced about the reality of the existence of black holes, these objects are by their very nature unobservable, and that in a much stronger sense than the inner part of the Earth. And the anti-realists will presumably deny that the evidence for black holes warrants the conclusion that they really exist. In their discussions of realism and related issues, philosophers have from time to time, but not very often, referred to cases from the history of cosmology. One can find as such examples the expansion of the universe and the Big Bang theory, but they are mostly used as examples that might just as well have been replaced by other examples from the history of science. I would also like to mention very briefly that sometimes the issue of realism, anti-realism, is connected with the demarcation issue, which in the case of cosmology means is cosmology a proper science, and what are the criteria that we are using. I realize that demarcation and realism are far from the same, and yet scientific discussion in the 20th century have often built on the premise that a theory, in order to be scientific, must result in truth claims or aim at discovering truth. If science is equated with truth finding, as scientists generally believe and generally believed, there is a kind of sociological or historical connection between scientific realism and demarcation criteria distinguishing science from non-science. And with regard to the scientific nature of cosmology, I will say just a few words about it, but I think it's necessary that I do it. And it's also not unreasonable to mention this famous work by Kant, 1781, because in this work he argues effectively that cosmology cannot be a science, that the concept of the universe cannot be an object of experience. And at any rate, these arguments they were widely understood by scientists in the 19th century as supporting the idea that although parts of the universe could indeed be studied by the astronomers, then the universe itself, one could not establish a science of the universe as a whole. I'll also briefly, yes, I don't know how well known this work is. This is a Jugendarbeit, not the first, but I believe the second of Kant's books. It's not perhaps that well known, but it's much more interesting from a historical and astronomical point of view than the other book. And Kant's attitude is entirely different. In here, in this Allgemeine Naturgeschichte, it's built on Newtonischen Grundsätzen. Yes, he adopts a kind of a realist attitude to the universe. Very interesting work, but apparently he changed his mind quite radically over time. I mention this also because these Kantian ideas about denying the reality of the universe or skepticism with regard to the scientific nature of cosmology is not only something that belongs to the past. They have, and possibly still are, have been defended by not only philosophers but also scientists. For instance, since the 1950s, an American philosopher, I'm not sure whether he's still alive, Milton Munitz, have argued at length that the universe is something which only exists because as a result of our theories and models of the universe. Without these theories and models, there is no universe. And this kind of skepticism or anti-realism that I have briefly referred to also played an important role in the scientific discussion, and especially in the 1950s and 1960s. In this epic controversy between two different world models, this was a period in which there was no paradigmatic foundation of cosmology. The relativistic expansion models, or Big Bang models sometimes, were confronted by the new steady-state theory of Hoyle and others. And in this discussion, as part of this discussion, it was not only physicists and astronomers who took part, but also philosophers or philosopher-scientists, and they took a very active and integrated part in this extremely important and interesting and instructive discussion, which I and other people have described at some length. You will recognize some important names up here. I can't go into the details, except that, I mean, this was the very subject which was discussed. Is physical cosmology a science? Discussed in one of the early issues of the new British Journal for the Philosophy of Science by Herman Bundy, one of the protagonists of the steady-state model, and Gerald Withrow, an astronomer and physicist who was a kind of neutral observer. Very interesting. And so, yeah, it's also worth mentioning that most, I think, in fact, all of the philosophers who took part in this debate adopted a skeptical or anti-realist position. And of course, in this discussion, as well as in later discussions and in recent discussions, obviously the concept of the universe was at the center of these discussions. And most cosmologists, then as now, took the universe to mean the totality of space-time and all the things which is in it. Although from an observational point of view, the universe is smaller. Most observational astronomers, of course, they more or less define the universe as what they can see with their telescopes. But it's interesting to point out that with the discovery of the expansion of the universe in the early 1930s, the very concept of the universe changed, that it changed rather drastically, and so that the concept became more problematic, at least as seen from an empiricist point of view. There are parts of the universe which we can see with our telescopes. So there's a technical horizon, which is not of any particular importance because it depends on the technological status of the instrument and so forth. Much more important is it that there is an optical horizon which corresponds, as you know, these objects, galaxies or clusters of galaxies recede from us, which is the essence of the expanding of the universe, and their velocity, recessional velocity increases with the distance. So at a certain distance, I mean, this is a very primitive formulation, so at a certain distance, they will recede from us with the speed of light and with superluminal velocities, which means that all these signals emitted from these objects can never be seen, not even in principle. And yet, cosmologists then as now had no problem with believing in these huge and perhaps infinite tracts of space-time from which there never can be any empirical, from which we never can have any empirical knowledge. This was pointed out with clarity by one of the great astronomers, astrophysicists, and science writers of the time. First, I believe, and by the famous Arthur Eddington. This is one of the early and one of the best articles, scientific articles on the expanding universe, which just at that time had been more or less accepted. And as he pointed out, in certain cosmological models, namely those models in which the velocity increases in time, the accelerating models. Then he says, in time the universe will become virtually a number of disconnected universes. So what he's saying is that if this model should be right, then it leads to the consequence that the universe cannot, in a certain sense, it should not be understood as a unique concept or object, but as a collection, and perhaps an infinite collection of disparate universes. So this is the idea of what during the last decade has been the subject of a huge discussion, the so-called multiverse. And again, I will refer to that only briefly, and mention that there are different kinds of multiverses. When I mention this, it's because that the questions of realism, anti-realism, becomes more problematic in these modern theories about many universes. Even if one agrees that that ordinary standard cosmology building on one universe that is in agreement with a realistic attitude, it doesn't mean that this realistic attitude can be carried over to the multiverse. This is an illustration due to one of the advocates of the modern multiverse, a Swedish-American physicist and cosmology, Max Tegmark, from Scientific American. There are different kinds of multiverses. We don't have to be concerned with the two on the right side. But this kind of multiverse is the simple and the uncontroversial one. That's the one which Eddington spoke of. But it's much more controversial. This kind level 2 multiverses, which builds in part on string theory, in part on so-called eternal inflation theory, and in which the various universes with these different colors, although they may have a common origin, they are causally disconnected. And what is much more strange is that they have different physics. They have different particle concepts, different laws of nature. The constants of nature are not the same, and even the dimensionality of the various universes differ. But let me leave these generalities and go back to more solid ground, to the history of cosmology, and try to illustrate how a realistic perspective on cosmology, at least in one important case, further advances in how to understand the universe. And I would like to point out that modern cosmology means essentially relativistic cosmology, based on the field equations that Einstein established in 1917. Einstein's model, original model of the universe, the great-grandfather of all later models, was static, it was closed, it was filled with matter. The same year, Willem de Sitter in the Netherlands came up with an alternative model which was empty in matter, but from the perspective of those days, it was also static and it was finite. Today, the de Sitter model is interpreted as an expanding model, but not from this period. And throughout the 1920s, almost nobody questioned that the universe must be static. There can be no systematic changes in the size of the universe. That was a sort of paradigmatic belief. In the very same period, as it happened just 100 years ago, the first redshift of galaxies were observed in Arizona by Melvin Slipher, whom you have here. And eventually, a fairly large number of those galactic redshift were observed. And in the 1920s, a few astronomers suggested that there might be a relationship between the observed redshifts and then the distance of the galaxies, and perhaps a linear relationship. But no one saw in this data the evidence for an expanding universe. One did, but only one. And incidentally, this is the best data from 1924, according to highly established Swedish astronomer Lundmark. And I think that one has to have a very good imagination to see a straight line between these data points. The problem was that the data were not good enough, simply. a couple of years later, this picture became very different. So it's probably well known that in 1922, the Russian mathematical physicist Alexander Friedman proposed the first dynamic models of the universe. But his work has often been misunderstood. It's true that in this later so famous paper in Zeitschrift für Physik, this is what today is called the Friedman equation, still the basis of cosmology. He spoke about expanding models, expanding and cyclical worlds. He spoke even about the creation of the world. But it's important to keep in mind that this work and his entire mindset was the mindset of a mathematician. He found all the solutions of Einstein's field equations and therefore the possible models, but he did not single out any of these models as particularly interesting or as the one which had the real universe as its referent. He apparently was just not interested in this one and real universe, and in his article there was not a single reference to astronomical or physical data. So it was very formal, and he did not single out the expanding models as more interesting than the contracting or the cyclical or the other kind of models. And in this respect, well, his attitude to cosmology may not have been anti-realistic, but it certainly can be characterized as non-realistic. And in this respect, he differs greatly from another of the pioneers in that area, namely Georges Lemaitre, who a couple of years later, 1927, in a certain sense duplicated Friedman's result, but in a certain other case went much further. The equations were basically the same. He rediscovered them independently. But he interpreted them within a realistic framework. And that, in fact, can be seen from the very title of this paper, in which it's homogeneous, the universe with increasing radius, and he explicitly refers in the title to the radial velocities of the extragalactic nebulae, that is the redshift. So he includes astronomical data and combines the data with the expanding model, and he fits this model to the data, and he even calculates what he predicts from his theory, the Hubble law, that the recessional velocity has to be proportional with the distance, and he calculates the Hubble constant 2 years before Hubble. That's what he's doing up here and here. The attitude of Lemaitre was very different from the one of Friedman, and it was also very different. Well, yes, this is the model of 1927, which was not a Big Bang model because it started in Einstein state, and then this state became unstable, and again, as a sign of Lemaitre's physical or realistic attitude, he tried to come up with physical mechanisms which made this original state unstable. His attitude to cosmology was different from Friedman's. It was also different from Edwin Hubble's in the US. Hubble, of course, was basically an observational astronomer, and he came up first in 1929 with much better results for the distances to the galaxies. On this basis, he made purely an empirical classification This is the first Hubble diagram. It's not particularly precise. It doesn't cover much of the depths of the universe, but a couple of years later we have a very impressive Hubble diagram which sort of proves Hubble's law. So I just want to point out that Hubble was an empiricist. He was even a cautious empiricist. He did not conclude or even suggest that he had discovered the expansion of the universe. And in fact, throughout his life, he refrained from supporting the expanding universe. He said, all that we have, this is our data. Our data shows that there is such a linear relationship, but it can be interpreted in different ways. Most likely, it's due to the expansion of the universe, in accordance with Einstein. But there are other possibilities, and so on. Yeah. Here we have Hubble and his collaborator Humason. This is Michelson, and this is some unknown scientist from the same period. And so, so in this period, it's also in the same period, namely in 1931, that we have Lemaitre proposing the very first idea of what later became known as the Big Bang theory. That's from 1931. And Lemaitre spoke about the beginning of the universe, again in sort of realist terms. He called it a primeval atom. So he imagined a huge super radioactive atom corresponding to the entire mass of the universe, which exploded radioactively. And according to him, it was more than just a sort of fiction. It was more than just a metaphor. He believed that it had happened in this way. All other cosmologists in the period had very different attitudes. So the common attitude in the 1930s, first of all, it was one of caution for understandable reasons. We have Richard Tolman, an eminent American cosmologist and physical chemist at Caltech, who in 1934 wrote a classic text, one of the first, in fact the first comprehensive works in relativity cosmology, and he emphasizes that we should distinguish between the solutions and the models, and then the actual universe. And most other people had similar ideas, and most of them, because of the realistic features built into Lemaitre's Big Bang model, this was a major reason why people in the period typically dismissed it. I have two examples of it, fairly typical. Let me just show this first. Just two quotations, both of them from 1933. Edward Barnes, a bishop and a mathematician, who considered Lemaitre's theory for nothing but a clever jeu d'esprit. And we have John Plaskett, a Canadian astronomer, who accuses it for being the wildest speculation of all. Other people in the period let me illustrate it in this way. I'm just saying that it was important for people in that period to distinguish between models which, from a formal point of view, started in a singularity. And then to distinguish this from models in which this singularity was meaningful from a physical point of view, such as the primeval atom of Lemaitre. These two, Einstein in fact was one of the first to propose the Big Bang model. He did that in 1931, and again together with de Sitter in 1932. This model called the Einstein-de Sitter model became a very important, almost for 50 years. It was more or less a standard relativistic Big Bang model. And it obviously is a Big Bang model. But in this paper by Einstein and de Sitter, they totally neglect this feature. It's very obvious that they don't like it. So they don't even mention it. And most people in the period didn't mention it either. So it took a long time until this attitude to cosmology changed. Yes. And now to another topic. But I think I'll do that briefly. Yeah. I don't know if 1989 is a long time ago from a philosopher's perspective. It's not from a historian's. But in those days, Jan Hacking, as a following up on his book, he wrote this paper on extragalactic reality. And the point was that he adopted his general idea of realism as justified by our ability to manipulate theoretical entities and to interfere with them experimentally. And then he confronted this sort of understanding of what realism is about and our reasons to believe in it with the astronomical sciences in general. Suggesting that astronomy and astrophysics did not qualify as proper natural sciences. That's what he says. They are model making. And the reason is, to put it briefly, that we cannot, for obvious reasons, manipulate with galaxies or stars or what we have. We can only observe them, so we cannot make experiments with them. And so on. A few years later, he retracted his claim, or at least he modified it, and these arguments were severely criticized by Dudley Shapiro in the same journal. To my mind, his arguments were convincing. I think most will agree. In fact, neither Hacking nor Shapiro mentioned cosmology explicitly. They mentioned astronomical phenomena, such as gravitational lensing. And gravitational lensing is not a truly cosmological phenomenon. It belongs to astrophysics. But surely, if we have reason for these reasons that Hacking indicates to doubt the knowledge claims about gravitational lensing and quasars and what have you, then it sort of follows that we had even more reason to doubt knowledge claims about the universe, which certainly is not something which can be investigated in the laboratory. I would like to emphasize the famous cosmic microwave background radiation, which is all important in modern cosmology. Discovered in 1965, predicted in 1948, and remarkably, this prediction was forgotten. So, but the point is that ever since its discovery, and until today, and for many years to come, first of all, this radiation from the depths of space is cosmological in the true sense. It doesn't come from somewhere in the universe. It comes from all over. And so it can be observed, but in a certain sense, it can also be experimented with. And this is what astrophysicists do. The signals, it's an electromagnetic phenomenon, of course, and the signals can be analyzed in the same sense that when physicists and chemists analyze the light from, say, the atmosphere of a star in the spectroscope. And by this kind of analysis, not manipulations really, but still analysis, people have obtained a very, very detailed knowledge of the cosmic microwave, its temperature or intensity, these inhomogeneities. It's a little hard to see why this kind of work should be observation in this passive sense. And from my point of view, it would qualify just as well as experiment. The last, I can't remember when I started. Go ahead. Okay. There is another reason for connecting experiments, real laboratory experiments with cosmology. Namely that, I mean, cosmology is basically the construction of mathematical models of the universe and then to compare the predictions of these models with observations. But experiment also enters, in some cases, very directly and crucially. And I would like to mention one particular cosmological model which was tested in the laboratory by means of precision measurements. It was not tested observationally at all. Everything went on in the laboratory, and it was found to be wrong. It's not well known, and there's no reason why it should be well known, because it survived for about a year or so. The electrical universe, at about 1960, the ever-inventive trio of the steady-state cosmologist, Bondi and his collaborators, came up with the idea that perhaps the numerical charge of an electron is not quite the same as the charge of the proton, because perhaps there is a tiny charge difference. If the difference in charge was greater than this number, then they could explain the expansion of the universe as an electrical effect within the framework of the steady-state theory. They liked this theory a lot, but it depended on this crucial assumption. And Bondi and Hoyle and their collaborators were sure that this was so small that it would escape the ingenuity of the experimentalist. But not so. Right away, a number of experimenters devised precision experiments of different sorts, different methods, different instruments, and they all came up with the same answer. That the hydrogen atom is electrically neutral. If it's not electrically neutral, then its charge is much smaller than this. Exit, this theory was killed. They tried to save it for a few months, but realized that the battle was lost. So certain cosmological models can be tested in the laboratory. This is not the only one, but it's the most remarkable example, I think. To end, more or less, I think that there are good reasons to adopting a realist attitude position in cosmology and to accept that our current standard theory, the hot Big Bang model, gives an approximately true description of the structure and the development of the universe. How far back one can rely on this model or consider it in a realistic perspective, I cannot say, but certainly a tiny fraction of a second after t equal to 0. Here we have one of these standard picture of the Big Bang theory, the magical origin corresponding to the time parameter equal to 0, sometimes called the initial singularity or the Big Bang sometimes. And people today have confidence in this model, certainly less than 10 to the 1 millionth of a second. And there are reasons for this confidence, of course. But I also want to point out, as I may already have done, that the closer we come to this magical point, the more problematic does it become for more or less obvious reasons. There are no data, essentially. And even the currently accepted standard model, what cosmologists today refer to as the standard model, includes the so-called inflation period. It's part of the standard model, indicating that the majority of cosmologists accept the inflation, or one version of inflation. But what went on before inflation and the so-called Planck time, in which sort of general relativity and quantum mechanics is supposed to be unified, nobody knows, which doesn't mean that there isn't a lot of proposals about it. And these theories, I don't see any reason why one should understand these kind of theories in a realist perspective. Not to mention the fate of the universe before the Big Bang. It's commonly assumed that the Big Bang was the beginning of everything. But there are half a dozen of theories, at least serious theories, probably wrong theories, but nonetheless serious, pre-Big Bang universes, some of them based on ideas from quantum gravity, that there was a universe which collapsed into, and then this collapse, or the time inverse of it, would be the Big Bang and so forth. Very elaborate theories, but whether they correspond to anything real or can be supported by data is questionable. In the same sense that it's questionable that the multiverse theories. So there is a class of cosmological models which is not in the same way supported, which one would not interpreted in a realist perspective. Nonetheless, and I will end now, I will end with a brief reference to the no miracle argument. I'm sure that we will hear a lot more in this conference about the no miracle argument, because it is a classical argument for realism, and it's still an argument, and it has been a great debate of it. It exists in various versions, and this debate will undoubtedly continue. But the essence of this argument is, of course, that if our best scientific theories were not approximately true, then the success of science must appear miraculous. I don't know if this argument generally is of any value, or whether it's supported by history or not, but perhaps the miracle or success argument is stronger in the case of cosmology than it is in most other sciences. For one should recall that in the 19th century it was generally accepted that there could be no science of the universe, that cosmology could not be scientific, and that similar skeptical attitudes survived the Einsteinian revolution with several decades. And so the success of physical cosmology, against all odds, is truly astounding, perhaps to such a degree that it can be taken to constitute a fairly strong argument for realism. Thank you.